All right, let's talk about where high-stakes finance crashes head-on with cutting-edge software engineering. Welcome to this explainer. Today, we're diving into exactly how we take incredibly complex financial frameworks, specifically highly regulated credit models, and package them up so they actually survive in the real world. Because let's be honest, we aren't just talking about writing the math or slapping together some code here. We are talking about making that exact code bulletproof, repeatable, and literally instantly deployable. So think about it for a second. How do you actually package a completely compliant, complex credit model into one single deployable unit? It is a massive, incredibly frustrating hurdle that data scientists and engineers are banging their heads against every single day. You've got these huge mathematical models that absolutely have to ensure strict algorithmic fairness, right? But you also have these interactive underwriting dashboards that people actually need to click on, use, and most importantly, trust. How on earth do you juggle all of those incredibly sensitive moving parts in a unified way so that it doesn't just instantly break the second it leaves the original developer's laptop? Well, to figure this out, we are looking at an absolute masterclass in model packaging today. It's a GitHub repository created by a developer named Manish Koti, and it's called credit_risk_sys. This is going to be our ultimate case study for this explainer. It's a completely end-to-end credit risk modeling framework. So this isn't just a quick script you run once. It's a full-blown system designed to ingest data, assess risk, and then output actionable, interactive results for underwriters. It is honestly the perfect lens for us to understand how modern mission-critical financial software gets packaged up. Now, the sheer horsepower under the hood of this framework is massive, but it comes with a pretty big catch. We're looking at some incredibly heavy-hitting technologies here. We've got XGBoost handling the core predictive modeling, SHAP ensuring explainability, so underwriters actually know why the model makes the decisions it makes, and Streamlit powering an interactive web dashboard. And to top the whole thing off, a whopping 98.5% of this codebase is written in Python. Python is incredibly powerful, for sure, but relying on all these specific interlocking versions of XGBoost, SHAP, and Streamlit, man, that means you are teetering right on the edge of dependency hell. If the environment shifts even a tiny bit, this heavily interdependent application becomes incredibly fragile.
And that fragility, that is exactly why packaging this application flawlessly is non-negotiable. It's not just about getting the app to run without crashing. It's about strict, unforgiving regulatory compliance. This specific framework adheres to algorithmic fairness standards and the SR 11.7 Model Risk Management Guidelines. And as we know, in the banking and finance world, SR 11.7 is the absolute gold standard for managing model risk. Let's really think about the stakes here for a minute. If you deploy this model and some background Python library updates without you realizing it, maybe changing a tiny rounding calculation deep in the math, actually, that is no longer just a software bug. No, that is a massive regulatory breach. An accidental drift in how your model calculates risk could lead to biased lending or flawed reporting, which could easily cost a bank millions in fines. Deploying it correctly with exact mathematical precision is literally the whole ballgame.
So to ensure that level of precision, we have to understand how this massive system is organized before we can even think about deploying it. Think of this project structure like an intricate assembly line in a highly regulated factory. First up, we have the data zone that houses all the raw and processed data sets, basically the raw materials for our factory. Next is SRC, which is really the brain of the operation. This holds the data pipelines along with the modeling and explainability scripts, crunching the numbers, applying the logic. Finally, we've got the dashboard area. This contains the Streamlit interactive underwriting interface where the finished product is actually displayed to the end user. These are distinct, critical functional zones, and they all need to talk to each other seamlessly. And that assembly line eventually has to produce results, right? Once the raw data passes through the pipelines and the models are trained, the outputs need a totally secure place to live. That's where the metrics folder comes in. It catches the output JSON files tracking fairness and feature selection. Then the models folder acts as a kind of vault where the actual serialized trained models are stored once they've been successfully generated. And finally, the reports folder takes everything and generates the PDF, regulatory, and executive summaries. Just think about how many moving parts are whirring away on this assembly line. You've got data processing, model training, precise metric tracking, PDF generation, and a live web dashboard, all running at the exact same time. Okay, so how do we guarantee this entire fragile ecosystem survives outside of the original developer's computer? Well, the answer is containerization. By definition, to be containerized means you've packaged your code and literally all of its dependencies, every single specific version of Python, XGBoost, Shop, and Streamlit into a single, completely isolated unit for seamless deployment. It's like, think about what physical shipping containers did for global trade. Before them, packing cargo onto ships was chaotic, fragile, and just unbelievably inefficient. This standardized shipping container revolutionized the world because it didn't matter if that container was sitting on a truck, a train, or a cargo ship. The contents inside remained perfectly intact, standardized, and totally isolated from the environment outside. Software containerization does the exact same thing for code. And the ultimate hero that provides this digital shipping container for our credit risk sys repository? That would be Docker. Docker takes this heavy 98.5% Python application with all of its strict SR 11.7 compliance requirements, its massive dependencies, and its multiple folders of interactive scripts, and it just absolutely locks it down. It creates an immutable snapshot. It ensures that the environment the code runs in is mathematically identical, whether it's being tweaked and tested by a developer sitting at a laptop in New York or being deployed at scale to a massive production server in London. The underlying hardware or operating system? It doesn't matter anymore, because the container provides the exact same environment every single time. So what does this actually look like in practice? Because the developer containerized this application, deploying this entire complex credit risk framework takes exactly 2 steps. Step 1, you just run the command docker compose up-build in your terminal. Docker reads the instructions, builds the environment, installs the precise dependencies, and perfectly wires that whole assembly line of folders together. Step 2, you simply open your web browser and hit the interactive Streamlit dashboard at localhost 8501. That is literally it. You don't have to worry about whether you have the right version of XGBoost installed or if your Python pads are broken. Docker just handles the whole shebang instantly. Which brings us to a final and honestly perhaps the most important thought to leave you with today. Does containerizing a 98.5% Python framework ensure algorithmic fairness is instantly reproducible anywhere? Just think about what we've unpacked here today. By using Docker to lock down every single variable, data pipeline, and mathematical dependency, we aren't just making software easier to install. We are fundamentally guaranteeing that complex, highly regulated compliant models will behave exactly the same way on any machine, anywhere in the world. It's a fascinating layer of reliability built right into the code, and it completely changes the way we think about deploying financial models. So as you look at your own complex projects moving forward, ask yourself, is your code just running, or is it guaranteed to be instantly reproducible anywhere?